Some functions have domain restrictions because particular values for the input variable cause the function to become undefined. Now you'll notice if you look at a few of these, well, all of these functions, actually not a few of them, every one of these functions behaves somewhat strangely at x is equal to 2. Notice right here, if I look at this function, I just have a weird hole right there. This is the function f of x. This is the function g of x. This one seems kind of disconnected right there. It's defined over here on this side, but not over here on this side. And over here we have a vertical asymptote at the point x equals 2, because if we plug 2 into this function, we'll get a 0 in the denominator. So this function also behaves pretty strangely at the point x equals 2. Now, keeping in tune with the last lecture that we had. In the last lecture, I said that one of the main things we're going to concern ourselves with in this class is finding the slope of a curve at a point. Now, the only way that we can do that is if we can describe the behavior of a function at a point. Okay, if we want to find the slope of a curve at a point, we need to be able to describe the behavior of that function at a point. So we're going to go through each one of these functions, and we're going to try to describe the behavior of this function at the point where things kind of fall apart, at the point where x equals 2. So let's start with f of x. So we're going to ask ourselves, how does f of x behave in the vicinity of x equals 2? You notice right here, here's my x equals 2 value. Now, if I want to describe the behavior of this function at x equals 2, well, one way that I can start doing that is describe the behavior as I approach that value along the x-axis from the left and from the right and from both sides at the same time. So here's what I'm going to do. I'm going to put a point somewhere to the left of x equals 2. I'm going to call this point x, f of x. And suppose that I'm going to allow this point to move. I'm going to slide it over. And notice this notation means as x, I'll write it, goes to or approaches to. Right? X goes to 2 or approaches 2. So what that means is that I'm going to take this x value and I'm going to make it approach the value 2. So I'm going to move it this way from the left. Okay, and notice what happens to this point as I move this x value towards 2 from the left. This point is going to shift along here. So I'll have another point right here, and another point right here, and another point right here. And my goal is to describe the behavior of this function as x goes to 2. Now notice what really happens here. Even though the function is not evaluated right here at this point, I have a hole right there, because if I plug in x is equal to 2 right there, this becomes undefined. I can still describe what the behavior of the function is. It looks like this function, as x approaches 2 from the right, then the function itself approaches the value 4. Right? The input approaches 2, the output approaches 4. So I can describe that with some specific notation that we're going to use quite a bit in this class. So let me write it out for you. This is the notation. I say the limit, abbreviated with this LIM, as x approaches 2 from the left. Notice that I have this weird little negative above the 2. It looks like a power, but it's not actually a power. It's a superscript. This is telling me that I'm allowing x to approach 2 from the left side of my function f of x, the red one. So when the limit as x approaches 2 from the left of this function, we're approaching the value 4. Okay, so what this is saying, the limit as x approaches 2 from the left of f of x is equal to 4. That means as I travel along this x-axis from the left, this point on my function is going to approach that value. Okay, so we say that this function behaves in this way in the vicinity of 2. Let me write it out for you. So I added some words to the screen. What this is saying in words, this notation is saying that our function output, the y value of our function, tends toward 4 as x approaches 2 from the left. Okay. So now let's take a look at what happens as we approach 2 from the right. So, and again, I'm going to put another point right here. I'm going to call this point x, f of x. Here's my initial x value. And I'm going to let that x value approach 2 from the right. And I'm going to observe what happens to the value of my function as I let x go to 2. So if I push the function, or if I push my x value this way, my point is going to travel along this curve and get really, really close. Even though I can't evaluate my function at x is equal to 2, I can still describe the behavior of the function. Now, the notation is very similar. So in this case, as x approaches 2 from the right of 2, we say the limit, as x goes to 2, instead of a negative, we put a little plus. That means from the right, f of x. Again, you can see as we move toward 2 from the left, our f of x value approaches the same thing. It tends toward the value 4. Now what happens if we approach x from both sides? Well, it looks like if I approach x from both sides, if I approach 2 from both sides, these points are going to end up at the same place. Same place. So let me write it out for you. Since the limit as x goes to x goes to 2 from the left of f of x is equal to 4, and limit as x goes to 2 from the right of f of x equals 4. So the left-handed limit, we call this up here, we call this a left-handed limit, and this is a right-handed limit. Since the left-handed limit and the right-handed limit are both 4, we can say that we can generalize and say the limit as x approaches 2 of f of x is equal to 4. Okay, we can only say this if the left-handed limit and the right-handed limit agree. For this function, the overall limit exists, like I said, because these two values are equal to each other. Let's try it again. I'm going to look at this function g of x now, and this function is a little bit different than the last one. Notice that we can't even evaluate, well, in the last one we couldn't evaluate our function at 2 either, but if I write this out, it looks like g of 2 might kind of be there and there. This is my point x is equal to 2. Okay, so let's play the same game that we did with the last function. Let's look at what happens to the value of our function, or the output of our function, as the input of our function approaches 2 from the left and from the right and then from the both sides. Starting out just like we did in the last problem, I'm going to take a point, I'm going to call it x, f of x, and I'm going to let that point approach the value 2. I'm going to let this point travel along this function as my x value travels towards 2 from the left. So what happens to this function as I get closer and closer and closer to 2? What is the value of the function doing? Well, it's actually staying constant. There's not really much happening. It looks like the value of the function is always just -1. There's a horizontal line at -1. So as I get closer and closer and closer to 2, it looks like, well, we stayed on -1 the entire time. So let's write it like this. The limit as x approaches 2 from the left of our function g of x, not f of x anymore, the blue function, is equal to, well, we stayed at -1 the entire time. Our output of our function stayed at -1. Our function is tending to the value -1 the entire time. We didn't go up or down, we just stayed on -1. Let's do the same thing from the right-hand side. So if I put a point right here, and I call that x and then f of x, and I let this x value approach 2 from the right-hand side, I want to look at what my function is tending toward as I do that. So go ahead and see what happens if our function just evolves like this. Well, it looks like the same sort of thing. As I approach 2 from the right, the output of our function stays the same. It stays constant. It's horizontal the entire time. So it looks to me like the limit as x approaches 2 from the right of our function g of x is actually equal to +1. We stayed on +1 the entire time. Down here we were down here at -1. Up here we're up here at +1. This is interesting because these two things no longer match. In our last problem, these values were exactly the same. In this problem, they are not the same. I have a different left-handed limit than I have a right-handed limit. So what that means is, if I look at the overall limit as I approach x, as x approaches 2 from either side of this, we're not approaching the same value. These two values are not the same. So here's what I'm going to say. The limit as x approaches 2, again, not right-handed or left-handed, just the overall limit of this function g of x. I want to be consistent here. We say that this limit does not exist. We say dne does not exist because we're approaching two different values as we approach from the left and from the right. Okay, so if I have a left-handed limit that does not match a right-handed limit, this is very important for us. If the left-handed limit does not match the right-handed limit, we say that the overall limit does not exist at that point. We can pick another point anywhere on this graph, and I could probably say the overall limit exists. But that specific point where we have that weird behavior, the limit does not exist, we're disconnected. Now let's look at the last problem. So again, I have this weird function where we have this vertical asymptote at x is equal to 2, and again, that's because if I plug 2 into this function, if I evaluate this function at x is equal to 2, I get a 0 in the denominator. We can't have that. We can't divide by 0. If you divide by 0, you'll destroy the universe. We don't want that. We all live in the universe. You can do it just kidding. We can say, just kidding. I divided by 0, but I was just kidding. But if you do it seriously, we're going to destroy the universe, so we don't ever want to do that. So let's play this same game that we did in the last couple of functions. We're going to ask ourselves, how does this function h of x behave as we approach 2 from the left-hand side, and as we approach 2 from the right-hand side, and then when we approach 2 from either side? Okay, so let's play this same game. I'm going to take a color, maybe one that I haven't used yet. Keep some variety. Again, I want to start off our analysis by looking at what happens to our function as we approach 2 from the left-hand side. So I'm going to pick a point on the left-hand side of this curve, and I'm going to call it x, and this is h of x. So I want to look at what happens to the output of my function as the input of my function approaches 2 from the right. So if I let my x value approach 2 from the right, I'm going to kind of just trace these dots up and see what happens. Well, we just go on forever. And we know that because a vertical asymptote means that if we approach some value, or if we approach some value where our function is undefined on either side, it's never going to cross that value, first of all. So it's probably either going to keep getting larger and larger and larger and larger and larger, or smaller and smaller and smaller and smaller and smaller. Hopefully we learned about vertical asymptotes at some point in our pre-calculus or algebra career. But I know that I can never cross that invisible vertical line because it's a vertical asymptote. Because at that line, if I evaluate my function there, I divide by 0. And again, the goal of finding these limits is to describe the behavior of these functions in a region. How is the output of my function behaving as the input of my function approaches a specific value? So for this particular function, it looks like that as I approach 2 from the right, the output of our function is just going to keep getting larger and larger and larger and larger, and I can keep getting closer and closer and closer to 2. I can always get closer to 2, but I can never cross it. I can get very, very, very close to 2. I can get infinitely close to 2, but I can never cross it. What's going to happen is the behavior of this function is it's tending toward infinity as we approach 2 from the left-hand side. So we say this left-hand limit of h of x, the output of this function is tending toward infinity as the input approaches -2 from the left. And of course, we have some symmetry here. We all love symmetry. If I pick some point on the right-hand side of 2 and I let that x value evolve, I let it travel towards 2 from the right, the same thing is going to happen. I have these points, and these points are just getting larger and larger and larger. As the input approaches 2, the output gets larger and larger and larger and larger and larger, and it just goes toward infinity. So again, the goal of these limits is to describe how our function is behaving in a region. If we want to find the slope of a curve at a point, we need to be able to describe how a function behaves at a point and in the region or in the vicinity of a specific point. So since we have the same behavior on the right, I'm going to say that the limit as x approaches 2 from the right-hand side of our function is also infinity. Now again, these two things are equal to each other. Infinity is kind of a weird concept. It's not a number. It's only a concept. You can approach it, you can never reach it. But since these two inputs are the same, just like in the case, these two outputs are the same, just like in the case of our original function, we can say that the right-hand limit and the left-hand limit are the same thing as each other. So as I approach 2 from the right and from the left, we get the same behavior. So this overall limit exists. And this function is tending toward infinity as we approach 2 from the left-hand side and from the right-hand side. Now, it's important for me to mention here that a function itself can never equal infinity. You can only approach it. You can never equal it. Now, limits, the point of limits is to describe the behavior of a function as x approaches a certain point. So this function is behaving in a certain way that leads me to believe that this function is tending toward infinity as I approach 2. That's all I have for you for this lecture. Look forward to seeing you all very soon.